Hi everyone! It's been a little while since my last update, sorry about that. I've worked on a bunch of things since February and it's just been pretty daunting to compile them all into one video, but that's what I'm going to attempt to do today. So we're going to cover a lot of different topics, the results of the first playtest with a paper prototype, reworking some aspects of the digital skeleton assembly to make it feel better, modeling a second version of our alien skeleton to make some tweaks following the playtest results, developing tools for an efficient Blender-to-Godot pipeline where we can easily create ourselves in Blender and they will be immediately ready for gameplay in Godot. And lastly, the most exciting part, coding muscle simulation in Godot to allow players to connect muscles between bones and see how the living creature would have moved. So let's get into it. Feel free to use the chapters on the timeline if you're interested in specific topics. So since the beginning of the year, I've been conducting playtests with the paper prototype version of Marsozoic, where players have to assemble this 3D printed skeleton properly and fill in the info sheet entirely, cross-referencing information from these books and documents they have available. I'm happy to report that they've been quite successful and full of insights. I'm really grateful to the small dozen people who sat down to play it, either solo or in pairs. It was really amazing seeing people interact with this puzzle I've created, discussing it and piecing things together from the available clues. The great news is that it seemed really engaging. I was obviously stressed about asking people to spend their time solving a complex puzzle, so I made sure they knew they could stop at any time, because seeing when people get bored of your proto is also really useful information. But most people actually sat with it for an hour and a half or even 2 hours until they solved the entire thing. And that's way more than I would have expected, especially for like a first draft proto like this. The survey responses on the engagement and fun aspect were also really encouraging. Here you can see that the responses on the fun front scored really high, again, more than I would have expected. There's a clear correlation too between whether the tester managed to solve the entire puzzle and how frustrating they found it, versus the amount of fun they marked down at the end, which is to be expected. This playtester also made the great point that the paper proto was extra fun because of how physical it was, because manipulating a lot of board gamey elements is always fun, and that I would need to test how well that holds up digitally. They're completely right, that'll be something to watch out for. The last piece of great news on the fun front is that the good fun ratings seem to hold up whatever level of experience and interest the playtester had in investigation games. Here you can see people with really different knowledge of games in the genre, but they all wrote down that they really enjoyed playing the proto. So this is all excellent in regards to the first question these first playtests were meant to answer, which was, is it fun? There definitely seems to be something there. The concept is engaging enough to people that they spent a significant time playing a proto version, with the caveat that we'll need to confirm those results for the digital version of the game. In terms of difficulty, it was also really enlightening seeing what people had problems with or not. The environment part of the puzzle was really straightforward for everyone, for example, because the hints there are quite clear.
Because ridges.
Oh, you got some map detail here, man.
Yeah, we found it here, eh? We see that these are ridges, which means that there was possibly water there. Movement of water, flow of waves.
While the locomotion, the creature using a large sail fin to catch the wind and glide on the surface of the water, that was a lot harder, because of course that's much more removed from the reality of Earth animals. So one person did figure it out. But that made clear that more outlandish concepts like that needed to be seeded a lot more with stronger hints. The feeding was an interesting case of also being difficult, but less remote as a concept, and the hints I introduced there seemed more effective, so people were able to deduce that one.
There's something significant about the fact that there's like a skeleton of another creature in here.
Well, an imprint, but yeah.
Well, in the imprint. So it's like, okay, is it eating like a skeleton, or does its like thingies have some kind of property that will then turn the thing into a skeleton and it like sucks up the juice? Like maybe it's like liquefaction.
Oh, I see.
Observing what people could and could not figure out was incredibly useful. It'll help me calibrate the hints necessary for each upcoming creature. One important signal that people were at least partly relying on their knowledge of actual Earth animals was the ribcage. In the proto-skeleton, I thought they would look more alien if I inverted the ribcage, like, oh, maybe Martian creatures evolved to have it this way around. Every single person playtesting turns the model over to have the ribcage the right way around, which then caused them some confusion. So unless this concept of an inverted ribcage is introduced more gradually in the game, it mostly misleads the players.
I think it's upside down.
Is it?
No, I guess not, because these are going down.
Well, we don't know actually.
I guess, yeah.
But like
Okay.
rib cages would typically go down, I guess.
Yeah, I guess that's true, yeah.
Lastly, I also learned that red herrings are just a bad idea. I had this piece here look too much like a skull, even though it's actually the sternum, and that caused the first playtesters a lot of confusion, so much that I quickly remade and reprinted that bone to look less like a skull, which solves the issue immediately in the next playtests. This imprint here of the tail tentacles also looked a bit too much like this picture of feelers in one of the available books, so a lot of players wondered if it was a sensory organ. Not necessarily bad, but it does show the importance of having hints be a bit more clear-cut. If they feel too vague, players will just hazard guesses in various directions, rather than having proper aha moments, which is really what you want to create in a game like this, right? So in conclusion, people generally found the deductions pretty difficult as they are currently, but most of them, given time, were able to solve the entire thing, except for the locomotion, which was just not hinted at enough. It's a good start, but I definitely want to rework and refine the hints available, so players can feel sure of themselves when they figured something out. I don't want them to feel like they've just kind of happened to find the right answer. You really want them to feel like the solution has suddenly clicked inside their brain. Besides conducting those playtests, I also continued work on the digital version of the skeleton assembly, to improve on the implementation and how it actually felt to manipulate. After all the experimentation shown in the last video, I finally got a better grasp of Godot's 3D rotation system, most importantly how to properly rotate objects around a specific vector in world coordinates, the vector that's pointing forward from the camera, for example. That allowed me to improve and simplify all the code to rotate the bones quite a bit, with fewer levels of nodes and reparenting needed, which gives us a much stronger foundation to work from for some more advanced manipulation features we'll get into in this video. I also refactored my movement and rotation features, following some excellent advice from the French Godot Discord community, which definitely deserves a shout out here. It's a great friendly group of people working on their own Godot projects and helping each other out. They pointed out to me that this class inheritance system I described in the last video could get messy and hard to maintain pretty quickly, with unneeded features being inherited by some objects, for example. Instead, they advised a refactor into a composition model, which Godot is especially well suited for. Where inheritance is a top-to-bottom model where your classes inherit features and become increasingly specific, composition is a bottom-to-top model where you create modules, essentially little bundles of features, and then attach all needed modules to an object to give it the features it needs. So in our case, we have objects that can move with a mouse and rotate with the mouse. So I bundled all the move with the mouse features into one module, and the rotate with the mouse features in another one, and then these modules can be attached as needed. For example, a book object needs to be movable with the mouse but not rotated, so it only gets the movement module. An object that needs to both move and rotate will get both modules. And then for fossils specifically, we need a few extra specific ways of moving, for example the ability to attach and detach from other fossils. So I made a specific fossil movement class that inherits from the basic movement class, and there. Now we have a composition model that allows us to give and take away features from objects in a really simple way. I also made a more noticeable improvement to skeleton assembly, straightening out the fossils when you attach them together. This stems from some comments on the last video already pointing out that it would be really annoying to attach bones together, only to have them be slightly badly aligned. This comment from Alejo Lab in particular suggested aligning the normals and attachment points in order to align two fossils' rotations on attachment, which really inspired the solution I ended up coding, so thank you very much. So in Godot, objects have a basis, essentially three vectors in space, the three you see here, which represent its local x, y and z axes. For example, if I rotate the object by 180 degrees around the z-axis, the y-axis of its basis is now pointing downwards. And so by knowing how each axis or vector of the basis is orientated, we know how an object is rotated in space. So what I did is I made sure that when placing an attachment point, I would orient its local z-axis away from the fossil like this, in the direction another attachment point would attach from, with the local y-axis pointing upwards like this. The attachment points then move and rotate along with the fossil when you manipulate it, right? And so I made it so when you put an attachment point over another attachment point to attach two fossils together like this, the local z and y-axis of the basis of the attachment point on the fossil you're holding align with the axes of the attachment point you're attaching it to, rotating the whole fossil along with it. And voila, the fossil's rotation straightens out according to the attachment point you're attaching it to. This makes it super easy and comfortable to assemble a clean skeleton, no need to rotate your fossils exactly into the right position. Of course, this reduces possibilities a bit and essentially gives you the proper direction of bones relative to each other, but I think this is a good simplification here. I'm not making a skeleton-free building tool, I'm making a paleontology deduction game, and I want the friction of the investigation to be more on how would these bones have moved and worked together, to do what, rather than, okay, what's the exact angle that these two bones should attach together. Essentially, not only should this make assembly more comfortable and pleasant, it will also focus the gameplay. With these improvements to the assembly system dealt with, I went back into Blender to make a new version of our test skeleton, one that would fully incorporate the learnings of the first playtest and have better topography, because the first version had some real crimes committed in the modeling process as I was figuring out what I was doing. Since making that first version, I've been working to level up my Blender skills a bit, especially by looking into the sculpting workflow. I'd never properly used it before, and as it turns out, it's a lot more intuitive to me, and it lends itself especially well to organic shapes, such as bones. There are a lot of excellent videos about the sculpting workflow, and using their methods, I was able to create a better, more organic and believable version of the test skeleton, with better topography and in much less time than the first version. As you can see, I gave up on the inverted ribcage for now. The ribcage is now the same way up as on Earth, so I made the ribs extra wide and flat for that kind of armored boat effect. I still have a ton of things to learn, obviously, but I felt a lot more in control and sure of what I was doing, and that feeling of skill progression was pretty awesome. As far as I'm concerned, it's a huge part of why I started off on my own project in the first place. When I was done making this new version of the model, I also tested adding a nice little decimate modifier to each piece to drastically lower the polygon count of each fossil and to give it this neat, slightly more low poly look. I think it makes it look quite cool, a bit more stylized, and it should allow elements important to the investigation to stand out more. During this process, I also decided to make a few basic assets to put in the Blender asset library for easy reuse, such as this vertebra and this rib. So from now on, whenever I need to create a new skeleton, I can start by pulling from this library of base elements and go from there. I can fill out the library with more and more bones as I go, and the added benefit is that starting each new skeleton from the same basic pieces before modifying them will make it that much more believable that these creatures have evolved from one another, since that's essentially what evolution does. It remixes a shared basic kit. I even created a simple vector displacement brush to easily add bone sockets when sculpting. That's what you're seeing here. At this point, I decided that it would be ideal to actually place all gameplay elements related to fossils directly in Blender when modeling said fossils, rather than having to import the fossil models in Godot and then add the extra gameplay elements there in the fossil scene. So for example, for the attachment points on the bones, it would be a lot better to be able to just mark them directly in Blender as I model the bones, rather than have to import the bones in Godot first. That would also mean that if I modify the bones later, I could just adjust the adjustment points directly in Blender, rather than having to first modify the bones in Blender, then go into Godot and modify the attachment points there. Basically, it would just streamline the process. So in the same templates Blender file, where I put my basic reusable bone models, I created an attachment point object and added it to the library, so I can easily link it into any file I'm working on. I put a lot of visual markers on the object to easily visualize its local axes when I place it. I can make this object look like whatever I want in Blender because it's just a marker. We won't actually import it in-game because we're going to tell Godot to replace it with an attachment point gameplay element. And to do that, I wrote a post-import script. So in Godot, when you import external resources, such as Blender files, you can specify a script to run just after the import that will immediately treat the data you just imported and set it up according to your needs, which can save you a ton of tedious setup work on each resource you import. Godot just imports Blender files as a new scene, and so if we write our import script well, we can just immediately have a working fossil that can directly be used in-game. So I started by having the import script add the fossil class to the scene we're importing, so it will immediately have all the features of a fossil in the game, the movement, the rotation, etc. Then the script finds all the attach point markers in the children of the scene. For each of them, it instantiates an attach point gameplay element, gives it the same position and rotation as the marker, and then it just removes the marker. And boom, a working fossil with working attachment points immediately on the first import. This was a perfect start to begin working on a new gameplay element, muscle scars. If you recall, muscle scars are marks on real-life fossils that show where a muscle used to attach to the bone. In Marsozoic, I want the players to be able to actually pull muscles between muscle scars to simulate how the creature could move. And so they need to be a proper gameplay element, but they also have to be drawn right on the surface of each bone. So our new Blender-based pipeline will work perfectly for that. Players will need to be able to select a muscle scar by clicking on it, so scars will need a collider sitting right on top of the fossil's collider, and of course they will need a different material from the fossil in order to stand out. So to make a scar, I can just draw it by selecting a bunch of faces on the fossil, duplicate them and separate them into a new mesh. I position the scar right at the surface of the fossil, and give it a different material to have it stand out, and then I just name it MS for muscle scar and add -col at the end to tell Godot that we want to generate a collider for those faces on import. And this here is now a muscle scar that we can set up in Godot. But all these small operations to create one quickly become tedious, so I decided to make a script in Blender to automate the process. So I looked into BPy, that's Blender Scripting API. And let me tell you, it is a bit weird. Instead of writing a script that will just do what you need behind the scenes, it feels a bit more like you're writing a script to manipulate the Blender UI like an actual user. It's a bit hard to describe, but for example, instead of having functions to do things like duplicate a specific object, you have to instead, in code, set the object you want as selected, like you would with a mouse, and then just run a duplicate operation. An extra funny thing is that the duplicate operation doesn't return the new object it just duplicated. So it's created, but you don't actually get a reference to it in the code. And here's the kicker. After a good amount of searching online, the generally agreed upon solution to that seems to be to save a list of all the objects in the scene before doing the duplication, then saving another list of all the objects after the duplication, and comparing them to find the difference, and the difference is the object you've just created. So needless to say, BPy takes a little bit of getting used to, but once you've got the hang of it, you can do really powerful things really quickly. Here's the script I wrote to automate all the operations to create a muscle scar. And then I made it into a button using this amazing add-on. So now I can call it directly from here while modeling. I select all the faces I want to make into a scar, I click the button, boom. Object created and named properly, different color applied, ready to be used in Godot. Speaking of Godot, we can now add muscle scars to our little import script. So when we import a fossil file, Godot will automatically identify muscle scars, give them the muscle scar class, and even prepare their collider by giving it the correct collision layers to make it detectable by the mouse. At that point, I was on a roll creating this neat little Blender to Godot pipeline, so let me round that up before I tell you how players can now use muscle scars in-game. So each fossil bone gets imported from a separate file, right? The skeleton is split up into parts to make a skull file, a left shoulder file, a left arm file, etc. But when you're modeling a creature skeleton, it's much easier to work on the entire skeleton at once, right? To see how the end result looks, how the bones fit together, where the muscle scars should go, etc. So I decided to structure my file so that the source file would be the entire skeleton file. That's where all the modeling work would actually happen, and in that file, each fossil, along with its attached muscle scars and everything, would be in its own collection. And then what the individual files would actually contain would just be a link to that collection in the source file. In Blender, when you link an element from a file into another file, you can then make changes to that element in the source file, and then the next time you reopen the file that links to that element, it will automatically be updated. So Godot imports the individual bones from those individual files, but the content isn't actually situated in them. It's all situated in the one skeleton file, where it's super easy to all update at once. But like I said, linked content only updates once you reopen the file that links to the source content. So to make sure the individual files that Godot uses were up to date with the source skeleton, I would have to reopen and save them every time I make a change to the skeleton, which kind of defeats the whole point. So I made more Blender scripts to automate that whole process. First, we have that simple little setup for Godot script that arranges everything in properly named collections, ready to be linked to by other files, as well as adds the -col suffix on objects that need a collider automatically generated by Godot on import. But then most importantly, I made these two scripts here that are able to automatically create or update the individual fossil files from the collections in this source skeleton file. So I just create the source skeleton the way I want, I hit setup for Godot to prepare everything into neat collections, and then I hit update all fossils, and Blender will create all the individual files, each linking to one of those collections directly into the proper folder in the Godot project. Or, if the files already exist, I just do all the changes I want on the skeleton, I hit that same button, and it will cycle to all the individual files to open and save them, making sure their linked content is up to date. As an example, if I have this arm here and decide to just go into the source skeleton file and modify its shape and add an attachment point here and a muscle scar here, then hit the script button to update that specific bone, boom, I go back into Godot and it immediately re-imports the individual file and reruns the import script. The model has updated and the attachment point and muscle scar immediately work in gameplay with zero further setup on my side. And thus we officially have a pipeline. And from AAA experience, I can tell you a properly set up pipeline can save you a ton of time and grief. It eliminates tedious tasks and risks for human errors, and it allows you to create content and iterate on it super fast. With these few scripts I've written, I can now create bones that will appear and function properly in my game in just minutes, instead of having to set each one up manually and individually update them every time I change something. So I was super excited about all this pipeline work. My former job as a tech designer involved some tool making, so it's something I have an affinity for, but I know most of you watching these videos are probably more interested in progress made in actual game features. So let's finally get to, what do muscle scars actually do in Marsozoic? Well, I made it so you can select them with the mouse like so, and when you click on them, you spawn a muscle that you can pull and attach to another muscle scar. The way this works is I just made a very quick little muscle model in Blender, then made it so Godot spawns that model when you click on a muscle scar and gets this bounding box. That's essentially the size of the model in the world, and in particular it finds this length here in the game world. That number is basically the normal base length of a muscle in the game world. Then on each frame that you're pulling the muscle, the script finds the vector between the scar you clicked on and the mouse position, places the muscle at the halfway point of that vector, and sets the z-scale of the muscles to the length of that vector divided by the normal length of a muscle we just found earlier. And here you go, the muscle scales on one direction between the scar and the mouse. When you attach the end of the muscle to another muscle scar, it does the same thing, but on the vector between both muscle scars. And now here comes the real cool thing. Once you have pulled a muscle between two bones, you can click on that muscle to contract it, pulling the bones along with it to let you see how they would have moved when the creature was alive. So obviously this was the real headache to get to work properly, and the thing I'm proudest of in this entire video. Because of course, now we're back deep in the swamps of 3D vector mass, where I can barely keep my head out of the water. So it was a real struggle to figure out the math involved and exactly how to code this. To summarize how this works, first I give the muscles a direction, because that was going to make the entire thing easier for me and for the players to understand. So there's a bone you pull from, that's the bone that you started pulling the muscle from, and a bone that you are pulling, that's the bone you're attaching the end of the muscle to. I gave the muscles this lopsided shape so you can easily keep track of the direction. So when you contract a muscle, the starting bone stays still and the target bone is the one that gets pulled. This also allows you to do funny things like this, if you like, by attaching opposite muscles in opposite directions. As to how the actual pulling works, first we find the pulled bone's attach point through which it connects to the bone where the muscle originates. I wrote a little function that can find a chain of bones attached together. So in this scenario, we look up the chain of attached bones from both attachment points, and we find that the bone we're pulling from is in this chain. So we know this here is the attachment point we want to pivot the bone around. As a side note, this even allows us to connect bones with muscles when they're not directly attached to each other, like this, which is also how muscles work in real life. If I do this with my arm, the muscle that lets me do this isn't here connecting my humerus to my radius. It actually starts at my shoulder connecting to my radius, and it contracts to let me do this. And now here comes the real headache, calculating what axis we need to rotate our pulled bone around on this pivot for the pull to make sense with where the muscle is pulling from. That part was the true struggle. I'll spare you the full details of me fighting to solve this problem. Basically, I figured out that we needed, number one, the vector representing the direction of the attachment point the pulled bone attaches to. This one here, that we've already been using at the beginning of the video to align bones together when they attach. And number two, a flattened version of the vector between the muscle scar we're pulling from and the pivot point. So this vector here, but then flattened in depth locally to the pivot point to essentially indicate the direction we're pulling from. And then we can find the vector perpendicular to those two vectors, their cross product. And that will be the axis we need to rotate around. In this example, that would be the vector going straight up here. And if we rotate the pivot point around it, the pulled bone will go left to right like this, which is exactly what we want. And then to clean up and simplify all the bones pulling, I decided that actually they should only be able to pull at these clean angles here, up, down, left, right, and diagonals. That should be plenty for most movements needed, and it will prevent weird rotation drift if a muscle scar is positioned slightly higher than the one pulling in the opposite direction, for example. So the last step is to snap that flattened direction vector to the closest vector at a 45-degree angle here. In this case, it's this one. We take this direction vector that the scar is pulling from, we take the direction vector of the pivot point, we get the vector perpendicular to both of them, and it gives us our clean rotation axis corresponding to the pull of this particular muscle, however the bones are rotated and attached. And there you go. Now you can pull and attach muscles however you want and make the bones move by contracting them. Needless to say, I was really happy when I finally got this to work how I wanted. Working on this also hugely improved my understanding of 3D vectors, so I no longer feel as helpless when it comes to them. There was one last important thing I needed to get working for this muscle simulation. The rotations need to be constrained. That is, a bone needs to stop rotating if it hits another bone. In order to do that, we need to be able to detect bones colliding. The bones already have a collider in order to be detectable with a mouse. It's a collider matching the mesh exactly, that's created automatically on import by using the -col suffix in Blender. However, you can't use complex colliders like that to detect collisions. You need simpler convex shapes. But we need the mouse collider to be very exact because the muscle scars are right at the surface here. If we make the fossil collider more approximative, it will eat the muscle scar collider. So I ended up placing two separate colliders on fossils, on different layers for different purposes. An exact collider for the mouse, and an approximate one using generated simpler shapes for the collision detections. And here we are. Now our bones stop rotating when they hit another bone instead of just clipping through. At the moment, I have the collision shapes generated automatically as part of the import script here. However, the automated generation doesn't deal well with some things, of course, such as bone sockets here. So I may have to actually create those colliders manually from simple shapes for each fossil to make sure they hit the important shapes and work to my satisfaction. And that's it for this video. Now we're in a pretty good spot with the skeleton assembly and the muscle simulation feature. I definitely want to move on to a completely new feature, namely including the reference books into the game, the ability to leaf through books, search specific words and concepts, etc. That will take us a bit away from 3D vectors as well, so I should be on firmer ground, which will be nice. Also, I want to mention that I will be at GodotCon on the 23rd and 24th of April in Amsterdam, so if you're also there and want to test the current version of Marsozoic, don't hesitate to say hello. Thank you very much if you're still here. Sorry it took me a bit longer to publish this video, they take a lot of time to make, and that's time that's not put into the development of the game, which obviously has priority. Making these devlogs is really enjoyable and also valuable because it forces self-reflection and it attracts early interest in the game, and people also give great suggestions in the comments, but it does take a lot of time to do properly. Initially I wanted to make about one video a month, and I've definitely had to drop that down to every month and a half or even every 2 months. I don't want to drop below that though, so I'll do my best to continue updating on my progress regularly. Thanks again for following along, and I'll see you next time.